but still so far. Can you still hear my heart falling with all my tears? I know, you know, we know. Yeah, we try and we try, but it's getting harder. For a while, paradise fell apart. Don't wait for me. No, don't let your love go to waste. Can't give what you need. One day I might feel the same. I don't know where I'm going. Wish that I could stay here to see your heart broken. Only thing I can say is don't wait for me. No, don't let your love go to waste. We gave it all we got. Sometimes it's not enough. I'll save the memories. I know you'll do it too. Yeah, we try and we try, but it's getting harder. For a while, paradise fell apart. Don't wait for me. No, don't let your love go to waste. Can't give what you need. One day I might feel the same. I don't know where I'm going. Wish that I could stay here to see your heart broken. Only thing I can say is don't wait for me. No, don't let your love go to waste. Oh, don't let your love go to waste. Don't let your love go to waste. Don't wait for me. Don't let your love go to waste. Can't give what you need. One day I might feel the same. I don't know where I'm going. Wish that I could stay here to see your heart broken. Only thing I can say is don't wait for me. No, don't let your love go to waste. Don't wait for me. No, don't let your love go to waste. Can't give what you need. One day I might feel the same. I don't know where I'm going. Wish that I could stay. I don't know where we are. When did we get it wrong? Where do we go?
All right, so today we are going to continue our series in discussing the modern processor design, and we have been talking about pipeline processors are still have trouble with hazards, and we hate hazards, and it's like our real life. Like yesterday, when I am coupling with friends of mine, I spend a lot of time waiting for people to come by. So I hate waiting, and as a programmer, as a user, you also hate the feeling that we have to wait for something to happen to finish. So that's why we care about those pipeline hazards. And we have been talking about structural hazards, which require us to revise our hardware design. We have been talking about control hazards, which we can use dynamic branch prediction to solve it. And today we are going to finish up our last piece about control hazard, and then we are going to start talking about data hazards. So before we start, again, it's always important for us to remember where we are coming from. And we are coming from the fact that although we have pipeline processors, and in theory, we want to achieve CPI equal to 1, which means that every cycle we can produce the result from one instruction. However, 3 types of pipeline hazards, structural hazard, data hazard, and control hazard, are preventing us from making that happen. And for structural hazard, we have been talking about stalls can address that issue, but again, it's really slow. So it turns out that this is what we do. We can write first, read later for register files. We can split the L1 cache. So that's why in your practice, there are so many examples that we use the split L1 cache. And even though you check CPU-Z, every processor you have nowadays, they do have the split L1 cache. And another thing that is interesting is that if we want to further avoid the structural hazard, we have to force all instructions to go through exactly the same number of stages. And so these are the 3 techniques that we have mentioned in making the structural hazards, avoid the structural hazards. And for control hazard, it's basically the source is because we don't know what the next instruction to execute. So it turns out that when you don't know what to do, you just predict, you just guess. So we have a branch predictor, which takes some of the outputs from previous executed branch and use that to judge what the program encounter. So these are what we have learned so far in addressing hazard. We have structural hazard, we have control hazard, right? And we have learned for control hazard, we have dynamic branch predictors, we have local predictor, like 2-bit local predictor that every branch has its own state. And we use a 2-bit saturate counter to keep those states. And if we guess right, there's no penalty. If we guess wrong, we just need to flush stuff. And then we learned, well, you can also use the history regardless which branch generate that result to guess what's happening. So that's another way of predicting, right? So for these pieces of a code, which in our local predictor, we always do a terrible job on branch X. Now we can have a perfect prediction no matter which branch it is. So this is where we are since the last lecture. And today we are going to continue talking about control hazards, and we are going to talk about data hazards and their remedies and the source of data hazards and see what we can do from the hardware. But before we start talking about data hazard, well, as I mentioned, we want to finish up our stuff on control hazards. So now here comes the question. Let me see by how much you figure out the predictor and your programs. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, so far I see over 50% of you thought it's C. However, as our experience, it's very likely sometimes the two that you guys thinking about are different from each other. So I suggest that we should start to discuss in breakout rooms. So let's go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, it looks like one of the group still consider the answer should be B, but the rest of you are concluding with the answer C. So I do want to invite one of the group to share your thoughts with us. All right. If I haven't heard anyone, then I will probably pick a team. All right. So we have the rocket team, which is anyone. So I have Akshit, I have An, I have Hassan, I have Michael, I have Rena, I have Dan, I have Vince, I have Yongwook. Anyone in your team would like to share your thoughts? Hello, anybody home? All right, Michael.
Yeah, I think our group was the one who went with B.
Uh,
That's because I think when you modulus it by 10, it's kind of like it's bigger than kind of like predicting a pattern,
mm,
how it was previously with modulus 2. So it's still a bit unpredictable. So I think that's gonna be kind of like they're kind of similar. Um,
mhm,
and for the next one, it's just it's kind of like the same thing as before, where there's it's they're gonna kind of be wrong initially, and then they're gonna kind of match up. And
mhm,
so for the third one, that's the one that I think will that G will do better
mhm.
um, because there's like a pattern from the inner loop and the outer loop, and then for the final one, because it's random, uh,
Mhm.
it's gonna be unpredictable. So I think it'll probably be like about the same.
Okay, so you mean for this one, everyone is probably about the same,
Um,
right?
yeah, yeah.
Okay, so okay, thanks for your insight. And this is what I thought, as you mentioned, right? The first one is about the same because an important thing for the history predictor to work out is that you need to have a sufficient amount of records to keep track of the history, right? However, here we are only changing our decision like once every 10, right? So it's probably unlikely that the global history predictor can capture that. And we are probably going to miss out every time when I is equal to I mod 10 equal to 0, right? So I don't think for this one, global history is too different from the local history, right? And for the second one, as you guys can both guess, is that well, there's only one branch, right? And if that's the only code that we are running, then both predictors should behave similar, right? The third one, right, which is similar to the example that was given in the last lecture, that this one changed once every time. So for local predictor, because it's 50-50, so it's hard for it to guess. However, for the history predictor, it can see if the last time is not taken, then I remember that pattern. So the next time it should be taken, right? So this one is indeed where G can outperform. So for this one, well, I would say local predictor might be better because the random one is actually mess up the history, right? So sometimes if you see this one is 1, 0, right? And or sometimes you see 0, 1, and it's not, it's very random that sometimes it's taken or not taken. So this one is actually mess up your history. So then it becomes really bad for the history predictor global history predictor to take any advantage. So that's the one that I would say the local predictor would probably be better because this is kind of like a noise to the history, right? So if you have a local predictor, this one is trained separately and this one is trained separately. So when you are maintaining the state of this one, you are not affecting by the noise here. However, not the case for the global predictor. So I would say local one is probably better. So actually, Rocket Team, you guys rock it. It's actually just one. So hopefully this question would give you some better idea about why we talk about both predictor, why sometimes we talk about global predictor, sometimes we talk why both are presented in a context of a class. And it also motivates the design of hybrid predictor, which is probably the mainstream predictor that we are using in our processors. So most processors right now not only just have one predictor, but actually multiple types of predictor or hybrid predictor inside. So one of the very classical example is called tournament predictor. So by tournament, it means that, well, we have multiple predictors and who was the champion for that? And we will use that one. So so saying that if you have two predictors, um, the tournament predictor, they still maintain a state. However, they don't use the state to predict the taken or not taken. Instead, they use the state to predict or say to tell you for this particular branch, which predictor would give you better result. So for example, you might have global history register. You might also have a local history predictor. And for a particular PC, if I found it says 1, then I would trust the result from one of the predictor that I have instead of just using that one as a prediction result. So this is actually a predictor because it's predicting which predictor would generate a more accurate result. And for example, if it's 1, then I may want to reference the local history predictor and take this result to decide if it's taken or not taken. So that's the whole idea of tournament predictor, which predicts which predictor is better, and the predicted predictor would make the decision. And in fact, modern processors, they have pretty complex predictors. And so we just presented a local 4-bit history predictor. So for example, the Intel Pentium processor, early Intel Pentium processors, they have local branch predictors with a 4-bit local history, which you can think is an expansion of the 2-bit predictor we presented in the class. And in Pentium M, very earliest Pentium M or Atom processor, they have the global branch predictor, which is exactly like the global history one that we presented in the class. And for tournament predictor, it was used in early digital alpha processors or AMD Athlon processor. And with the latest AMD Ryzen processor, they have, or the Samsung mobile phone processor, they have even have a perceptron-based neural branch predictor, which is pretty fancy. But for this class, it's just good enough for you to know that, well, here are the basic ways of making branch predictions. And you know there's someone in your code, or there is somewhere in your processor try to guess the direction of predictors, the branch. However, they are not perfect. So it's really important for us to make our code align with the behavior or make our code more predictable, right? So now, if you remember the demo we have, right? Like the option 1 is faster, right? You probably can know why. And sometimes you will feel that, well, I'm not writing this kind of code. Professors, your demo code doesn't work, doesn't let me feel like it's relevant to my life. So so yesterday I thought, well, we can probably use a different way to present exactly the same demo that I want to present you here. So I believe many of you would like web programming, and a lot of front-end web operations are based on the backend support from the database. So a lot of you might be familiar with this syntax. So this is an SQL query. Try to count how many items in a table are larger than value B, but smaller than the value A. So for this particular demo, I can show you this. So I have a database table which consists of the following item. So we have 3 columns, and the last column is the value that we want to look for. And as you can see, they have integer values that ranges quite a lot. Now I have a script which I drop the table first, so that you know there's nothing in there. And then I recreate a table. And for each of the table, I try to read the file that I mentioned and that I just show you. So then when I create a second table, instead of faithfully insert every element, I sort the elements by ascending order. So now the last 3 things that I would do is that for each of the database table, I perform 3 identical queries and see what the performance result. So now let me run this demo for you. So for this demo, in the very beginning, we are just trying to insert those. And as you can see, right, ignore the first one because there are some caching effect due to the previous query. But let's look at the second query and a third query for each of the data table. So this is, we run second query on the unsorted table. As you can see, it takes 413 milliseconds. And for the third query on the first table, which is unsorted, it takes 77 milliseconds. However, for the sorted table, if you just want to find the range, the items that fulfill the range of the values, it only takes less than 5 milliseconds, regardless which how big the range that you are querying. So it tells you how efficient and how important is it that even in database, if you can keep the most important or say the most frequently queried column sorted, that will help you a lot in performance. And there is a reason, right? So now I am asking you, what's the reason? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now it's kind of interesting, right? Let me share the results. So B and C is kind of like a tie, and D is also not a bad answer. So why don't you guys go ahead and discuss in group, and let's see if there is any chemistry would change after the discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so is there any group who would like to share your thoughts about this question? Any group would like to share? Somebody home? So after the discussion, it seems like more of you leaning toward B. Some of you are still insisting it's A. Okay, Vince, you got it. That's also rock, Tim. You
So
guys
to,
rocks.
so to be honest, I'm not too sure on the amount, but
Well, that's okay. I
okay.
love it. Right.
Okay, but I think
yeah.
statement 3 is correct.
Statement 3 is correct. Why
think.
is that?
Because since the data is sorted, like
Mhm.
whenever how do I explain this? When data the elements in the array are within, or like they meet the condition,
Mhm.
all the ones that are true will be like next to each other or contiguous. And
Mm.
so the branch prediction will be easier to predict the correct branch in contiguous pattern, I guess. I don't really know how to explain that well.
Right. So yeah. So maybe it's easier to say, well, for this particular branch, right? Because your data is sorted, right? So you can and you know our predictor is like, even though you have a local predictor, right? Then this one, right? If you have your data sorted, everything before the threshold is the same direction, and after everything after the threshold is the same direction, right? And once you retrain the predictor, every prediction should be similar. And if you have a sufficient amount of data, right, you have almost 100% prediction rate. However, if your data are unsorted, then this is like random, right? And if it's random, sometimes bigger is smaller, right? So it makes the branch prediction very difficult to predict. Agree?
Yes, that makes
Okay,
sense.
so do you mind to walk through each statement with me? So what do you think about the first one?
The amount of dynamic instructions needs to execute is a lot smaller. I'm not sure about this one.
Okay, so why don't you, what prevents you from being sure about this one?
So I don't know, this might be a dumb question, but I'm not too sure what dynamic instructions are.
Okay, so if you remember in one of our lecture, I have a loop, right? And I were asking like, well, the loop has only 5 instructions, right? But I were asking like, okay, if I execute the loop for 100 times, how many dynamic instructions are executed? Now, do you have the memory what dynamic instruction?
Yeah,
Right? So dynamic instruction means
the total number.
what of the instructions are actually, or the instance of instructions that are executed by your processor, right?
Oh, right.
So for this particular case, do you think when option is 1 or say non-zero, is it going to have fewer instructions or more instructions?
Well, since it has to sort, it'll obviously have to do more instructions.
Right. So it's
So
actually more instructions, right? And remember, each equal to IC equal times CPI times CT, right? So this one is definitely making the performance worse, right?
Right.
So this is not a factor make the performance better. How about the second one? Do we change the amount of branch instruction?
No, it'll be the
Not
same.
really,
Not
right?
really. It's
Well,
just
and in fact, if you count the ones in a sort, it's actually going to be more, right?
right.
So how about the last one?
Well, I don't think that's true because you still have to check each element in the
Right. So for this
array.
particular loop, it's not reducing, right? And
Right.
if you consider the fact that I have to sort it, it's actually going to be more, right? All right, Vince, thank your answer, and you give Rocket Team another credit. So here is the thing for this particular question, right? Okay, Doc, you have a question. Let me see what is that. So you said that if we have smaller upper bound for I, option 0 will be faster. Well, so the thing is that, right? If U is cute, so the key thing is here, right? If U is cute, this query sufficient amount of time. If you are not just querying it for just one time, then it becomes obvious that, well, and the other thing is that for this one is random, right? So still, right, the branch prediction would be still can be easier to predict. So considering that when you sort this for just one times, but you have to execute this part for many, many times, then the second part is going to be more critical. All right. So hopefully that would address your question. So then you can imagine, right? What happened is that for this particular branch, let's call it branch X, without sorting the accuracy, okay, even though I have the best ever predictor, right? I might be able to guess it for half of the time, right? If I like I stupidly guess just one direction, right? That's probably better than random guess for this case. I can only get like 50%. But if you sorted it, the accuracy would be 100%, right? And so that's why for the branch X, before threshold, after threshold, using sorted data would make the branch behavior a lot better. So that's why for this question in particular, it's because of the branch misprediction. And if you don't trust that, right, then we can definitely run the demo one more time. Let me see, not this one. I think it's probably in the very beginning of the quarter. And this is the array sort example. And let me take this dash PG out. Okay. So for this array sort example, and remember, well, let me see what's my command line look like. Okay, 262, 144. Okay. So our best friend, perf. All right, let me run this amount of time without sorting. Oh. Wait. Seriously, I forgot my password. Oh, here we go, right? So without sorting, we have 8.88% of miss rate. If you're Chinese, you are probably happy with this number, but you know, as a computer scientist, you definitely love this number, right? So if you have the data sorted, as you can see, the branch misprediction rate is only 0.03, right? And sometimes you might think, well, 1,000 is a large number. Okay, let's try. Well, 10,000 is a large number. Let's try 1,000, right? And with 1,000, you can see the branch misprediction rate of the code is still like 8.67% and still less than 1% for the sorted data. So you know the power of sorting, and the performance difference is significant, even though I now only change my number to be just 1,000 queries. All right, So hopefully that would give you a good idea about how important is it to sort your data because of the existence of branch predictor. So now, originally I am thinking about giving more code examples about how to optimize your code because we have branches. However, I also found we can probably combine that into a better or more fruitful session after we discuss the data hazards. So I will start the data hazards. So it will become another. So later on, we will have a lecture talking about how to optimize your code on modern processors. So right now, let's talking about data hazards, which is one of the three critical pipeline hazards that we have. So data hazard is one type of hazard that because of an instruction currently in a pipeline cannot receive logically correct value for execution. And why am I saying the logically correct? You can always get the value from the register. There's no problem with that as long as you don't have structural hazard. However, it's uncertain that if the value you get is correct or not at the time that you fetch the data. So definitely that's not what we want. You don't want undeterminism in your code. So that's why we want to make sure that every time when an instruction fetches values, they are logically convincing. So it's very important to make sure that when you execute the instruction, your later instruction follows the data dependency in execution order to make sure that I can always get the output from an earlier instruction as an input if I am depending on that one, right? However, if the later instruction that consumes the result is still in the pipeline when I want to use it, I have to wait, right? So that's code. That's when we have data hazard. So to judge if there is a potential of data hazard, it's important to see if we have data dependencies first of all. So for this particular code, which you might already be familiar with, is the code we use for swapping. Can you tell me how many data dependencies, how many data dependencies are there in this pieces of code? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looking at your answers, I guess it's probably a good chance for us to discuss in groups. So let's go ahead and start our group discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. All right, so looking at your answers, I do, well, looks like we are still kind of diverse. So is there any group who would like to share your insights with us? Any group would like to share? All right, Vince, you rock it.
Okay, our group thinks it's B2
Okay, what are the
because
two?
in the third move instruction, the value at register EDX is being written into the register RDI. But in the second line, it's being written too, so it has to wait for that to be written in there. And then
Okay.
also for line or the fourth move instruction, the register EAX also needs to wait for the first move instruction to, yes.
Okay, so we got two. Any more? First call, second call, third call. Okay, deal, right? It's indeed two, right? So this one, right? So there are two pairs of data dependency. And we have been talking about there's another implementation of swap operation. So can you check how many data dependencies are there in this version? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so definitely I see a demand of group discussion. So let's go. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so any group would like to share your thoughts because so far I see two popular answers. Well, before we have any team sharing that, right? Some of you might be thinking about, Professor, are you seriously? Right. So here is what I just generated. If I use GCC-S-03, the swap.c code, which we have in the past, the reg swap and the exclusive OR swap. And this is what generated. So these four instructions are indeed the reg swap. And those are indeed the XOR swap, right? So those are indeed the code that were generated from both code segments. So now I'm asking you, how many data dependency do we have there? Any team would like to share? All right, if not, then I will pick one. Oh no, Rocky team again. Vince, do you want to share? I know
Okay.
you are the... Yeah.
Our group is gonna go with C3.
Okay, so what are the three that you guys have in mind?
So the third line, the register EAX, is dependent on the second line to be completed. And
Okay.
then in the last three instructions, the last two instructions rely on EAX to be written in yes, those two, yes.
Okay, so those are what you have already identified. So tell me about your understanding about the syntax of exclusive OR in SAT6.
Okay. I'm not sure, to be
Okay.
honest.
Okay, so I guess if I tell you exclusive OR L, let's say like this is A, this is B, right? That actually means we are doing this. Then would that change your answer?
Oh, yes.
Okay.
So then also the first and second line. So the second line depends on the first line then.
Mm-hmm.
And then also
This one, right?
oh yes.
Right. So actually there's a total of 5. And you can see it's terrible in a way that they are all back to back. So you can imagine, right? If we cannot address this, if our pipeline cannot address this very well, then that tells you how bad the performance of the right-hand side code is, right? So again, right, if we try the idea of stall, right, which means that whenever we have a data dependency that cannot be solved, we just stop, right? And here's the performance with the code with a better the better version of a swap, right? Even with the better version of the swap, well, if we can pipeline the memory operations again, right? Before this guy's being writing back, right? There's no way that we can, well, so for this sequence of instruction, right? Before the EDX is writing back, if there's no appropriate hardware support, we cannot do anything with the later instruction, also this one, right? So the whole pipeline gets stuck for this. And you can see there are 2 cycles of stall because we have to wait for the data to come. However, but if you are careful about that, right, you will figure out that At this point, we already have the value of EAX in our memory, in read from the memory. At this point, we already have the value of EDX that's already read from the memory, right? So why can't we execute this a little bit earlier, right? So that's one question we have. So the hardware solution to this is actually called data forwarding. The basic idea of data forwarding is to add logics and wires to forward the desired values to the demanding instructions whenever we need. So this is the original pipeline that we have with branch prediction. And with data forwarding, you can imagine that we have additional wires to forward values from memory operations to whatever ALU that needs the value, or from arithmetic logic units to whatever other unit that needs that value, or have that value to any other units that we needed, right? So that's the idea of data forwarding. And because this is 142, I'm not going to ask too much about the detailed design of the data forwarding. You just need to know that, well, there is some magic in the hardware that can now forward the values to the functional units whenever the data is produced in a pipeline, right? So with that in mind, and let's assume if a memory operation takes 2 cycles to generate the result, which means that exactly like the pipeline that I show, we have 2 stages of memory operations. Then how many of the data dependency that we have would be problematic, meaning that it would become data hazard? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I guess we can probably have a brief discussion among you guys. Have I shared the question? No, yet, not yet. Okay, so let's have a brief discussion still. Go. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now let me show how many of you would like, well, any of you would like to share your discussion result? Well, if not, I will probably have to pick a group too. All right. Before it stops, any group would like to raise your hand and share. All right, Team Blue. We have Adam, we have Anthony, we have Chris, we have Humboldt, we have Louis, we have Teme. Somebody home. Somebody in Team Blue, can you guys share your insights? Hello. We have Chris, we have Anthony, we have Humboldt, we have Hong Hao. We have Adam, we have Louis, we have Teme. Do you want, or do I need to pick one for you? Well, if you don't have a consensus, that's fine too. Anthony, do you want to unmute yourself?
Professor, we weren't really sure how to approach this problem because there should be a difference from the previous one, but we aren't exactly sure how the changes would take place.
Okay.
So, I mean, I was guessing that it should be one less because there should be an improvement from the last.
Okay, that's a good guess. Right?
Right. So I guessed one B because last time we had two because of the EAX to the EX and EDX to the EDX because we're storing it and then we're calling it again, which would cause a cycle delay. This time it'll take 2 cycles and it's 4 cycles. So because it's more problematic, so it's still problematic.
So maybe we can go back to this one, right? How do we know we have to stall here?
Because it's not finished. EDX is not finished by the cycle.
How do I know it's not finished?
It's still in the write back stage, I believe.
Right, but how do I know if it's still in the write back stage?
Isn't there like a hardware flag or something from?
Oh, so the thing, well, the easiest answer is that because we draw the diagram.
Oh, okay.
Right. So because your question right now is that you don't know how to start, right? So let me tell you how to start, right? First of all, right, we are fetching it, right? We are decoding it, and at this time we are fetching it, we are decoding it, right? So these 2 stages should be fine, right? Now I am doing the memory operation, right? This should be fine with the first 2 instructions, right? And then now I'm in a second operation. And for this one, this is another memory operation. Is there any conflict with the first one?
There's not, I think. There's no conflict.
Right, so we can see, right? Now, for this particular one, it depends on the value of which one?
EDX.
EDX. So in the next cycle, right, is the memory operation generating EDX ready yet?
It's not ready yet, I think.
It's not ready yet, right? So even though we have the hardware for data forwarding, there's nothing we can do, right? So you cannot do M1 because if you do M1, you are going to get some random value. So you have to stall here, right?
Yeah.
Okay, so then we keep going, right? Now in the next cycle, right? This one go into M1 and this one go into decode and this one go to M2. At this time, can we have the last instruction go into M1?
We can, I think, because it's done.
Good, right? Because it's
Yeah.
done, right? So here's the thing, right? Although there are two data dependency, only one of them will cause a stall. That's this one. Now, do you know how to solve this kind of problem?
With the NOP. So it's just one, right?
Right, it's just one. But now, do you know what's the procedure, or say what's the right steps toward the solution of this question?
Yeah, I think so. I was
Okay,
confused about
so
what was the difference from like what's the difference in the problem from the previous one again? Like what caused the
so the previous problem is simply ask for data dependency, right?
Oh, I
But
see.
this one is actually asking how many data dependency would cause stalls.
I see.
All right, so let's try one more question. This one. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now for this particular question, I believe it will be really beneficial if we can go into group discussion. So go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so this time I have Anthony raise your hand, standing for the group blue. Do you want to share your thoughts with us? Feel free to unmute yourself.
So for this one, I put E4 because we see that the did you say something?
Yeah. Keep going. Hello?
So we can see that it takes 2 cycles for the move, and then 4
Mhm.
cycles, 3 cycles for XORL. So we see that we put down the pipelining stages. So for the first one, we can see that IDIF. The first one and second instructions have nothing in actually they write backstage because they both write back to EAX, right? So I think that there's no conflict between these two because there's no data hazards.
You
So
mean
we
the
can just
first one and
first one, the second one.
the well, actually there is, right?
Oh, there is.
Because remember the syntax that I mentioned, right? This one is actually EAX. It's calculating EAX equal to EAX exclusive or RSI.
With those two.
Yeah. So does that change your mind?
Well, there's no more than, or there's nothing. There's not an
Four,
option that's
right?
yeah.
So okay, so right, but in fact, right, so but you are definitely on the right track. So there is a there are such data dependencies, right? And as we mentioned, and first of all, as you mentioned, right, for the first couple cycles, it looks like this, right? Now, the first instruction, we can have it go to the M1 stage, and the second instruction is still in decoding. And now, but because there is a data dependency, right? So, no, all right. Because there is a data dependency, right? So the second instruction cannot directly go into its execution or say, because we want to get everything ready before we can execute it, right? And the M2 is not finished yet. So even though we have forwarding, there's nothing we can do, right? It's like you are asking people, give me what I need whenever it's ready as soon as possible. And you keep asking, can you give it now, right? But your source is actually, it's not produced yet, right? So how can I give it to you, right? So you still have to stall, right? So that's what happened here, right? So turns out you have one cycle stall. So this one is still problematic, right? And even though you have data forwarding, and if you keep going on, you'll figure out that as Anthony just said, right? Because it takes so long to create those values. So it turns out that this all of them, right, except for probably the last one, because for the last one, the EAX is already generated here, and it has sufficient amount of time to finish. Except for the last one, every data dependency would still be problematic. So Anthony, you guys are on the right track. Give you guys an applause. Yay, good job. Right. So here's the thing, right? You can see that's why this pieces of a code is not doing well on so that's why we said that, you know, for performance optimization, we don't want you to write this kind of code, because even with pipeline, right, this is really bad, right? But the stupid code, or I shouldn't say it's stupid, but the simpler code actually is more powerful than this fancy code in some sense, right? So sometimes people will think performance optimization is to make your code something difficult to understand. That's not necessarily the case. It's case by case. It's all what we want is to make your code more efficient. So we have learned a lot about pipeline. So I just want to ask you a very high level concept question regarding the pipeline. So regarding pipeline, this is probably a good summary. What do you have learned? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, let's go group discussion. All right, let's wrap up in 5, 4, 3, 2, 1. Time is up. Okay, so looks like we have a pretty diverse result. So can I have any group sharing your thoughts with us? All right, Anthony, what do you think?
I think there's only one this time because
Okay,
first
one?
one, I think it's just C or just number 3.
Number 3. Okay,
More pipeline.
the more stage. Well, because you saw it, right? So how about the first one? Why do you think it's incorrect?
Since it says we can only fetch one instruction or cycle, the optimal CPI pipeline has to be a little bit more than one, because if there's multiple pipelining stages and each one, like if we draw a diagram, there should be more than one stage, correct? So that will already be more than one, right? If there's more than one stage.
Okay, Vince, you also raise your hand. Do you have a different opinion?
Yeah, I think one is actually true
Okay.
because if we
Mhm.
do, assuming that the pipeline has no stalling problems, since you're fetching an instruction every time, you should also be
Mhm.
like at some point, like after however many stages you have, there should be a point where you just keep finishing an instruction every cycle.
Right. So Anthony, do you agree with that? Just like the slides, right?
Yeah.
Do you remember this one, right? Okay. So regarding the second one, what do you guys think?
I think
I
that
guess
one is
Anthony
false.
told no, and you think it's false. And the answer is yes, because the fewer amount of stuff that we have to do. That's why I'm saying that if you can evenly distribute your task, right? The shorter the cycle time, because the cycle time is depending on how much stuff you have to do within a cycle. The last one, Vince, do you have what's your opinion?
I said this one was true too,
Okay, why?
because I think if if the predictor is wrong, that means it did more stages for other instructions that are just going to end up being no op instructions.
That's
But
actually correct, right? So actually, regarding pipeline, these are the four things we have to learn. So that's why we want a better branch predictor. That's why we want to deal with data hazard, right? All right. So I hope this will give you a pretty good idea about pipelining. And in the next lecture, we are going to talk about some more advanced stuff. And before you leave the classroom, there are actually something that I want to tell you. First of all, assignment 4 due this Sunday, and it's already on Gradescope. And last reading quiz. Wow, time flies. Due next Monday. The last chance for you to boost your quiz grade. And regarding final exam, it will start from 1 p.m. Friday and 1 p.m. until 1 p.m. Saturday. Any 3-hour slot you pick. And so the reason why I have it lasting starting from 1 p.m. Friday is because I believe some of you do want to ask questions during my office hour on Friday morning. So use that chance. And probably a good news for you that I know because the original deadline of left 4 and left 5 not left 4, not left 4. The left 5 program assignment was originally scheduled to be on Friday as well. So we can extend it to Sunday night so that you guys have more time to focus on your final. All right. Other than that, enjoy the rest of your day. I will see you tomorrow.